Hi guys, this is 20.2 Modeling and Density for Geometry. All right, so our essential question is how can you model real world situations involving density? And our shortest possible answer is basically just determine the area. So if we're talking about people or population, we're talking about a certain plot of land, all right? Or, basically area that we're talking about with those humans inside it, or even just atoms. So if we're talking about different objects and their atomic scale for area, that's something to consider. Or volume that's involved. So volume would be like, let's say you have a tank, and that tank has a certain amount of volume to it. All right, and basically you're just going to take the area or volume and then divide it by the total number or quantity by the area or volume. So the number of people, okay, or just the atomic scale, aka mass. So that's something important, or quantity, okay, by the area or volume to calculate the density. So let me show you what I'm talking about. So again, let's look at the word density. Density is the amount of matter that an object has in a given unit of volume. And it basically can be calculated by this. You take, to find your density, you just take the mass and divide it by the volume. Okay, so density can help us compare different objects with different materials. Obviously, if you had a cubic foot of wood and then you had a cubic foot of lead, you would realize the lead, it definitely weighs a lot more than the wood. Okay, so there's a big difference there in not just density but also in mass. Even though they take up the same amount of space, they don't share the same density. So let's go ahead and apply this to the real world. Okay, we're going to compare two different types of wood. Now that's very important to note because you see some people not care, like construction workers, they're not buying tons of balsa wood. All right, that's not a very high structural integrity type wood. That's not going to hold up a house, especially if it's 2 stories. Balsa wood is like, you're going to use that for a little model airplane or something like that. You're not going to use it to build something. So again, we use different woods for different things. All right. Whenever they had the kings in old Europe go to war, the grandfather would usually plant an entire forest of oak trees, and they'll just basically like tell everyone like this is for my great grandson when he wants to go to war, because they would cut down the oak trees to build ships. So that's pretty crazy. Where thanks, granddad. I knew he didn't trust the French, and next thing you know, they cut down all those oak trees and they go to war. So they actually do that. Each type of wood has its own purpose, especially back then. Still today. All right, so let's make a prediction. So this is part A. Let's make a prediction. Let's figure out which wood's denser. Now, you probably look at their masses, right? And you're just like, oh, American redwood. I think that's going to be the most dense. But then again, we have to take into account, well, how big are these logs? Okay, so we actually have to consider their volume. So this is where part B comes in. So at first, you're probably thinking redwood, right? If I can spell it, redwood. There we go. All right, because of the mass. So let's figure out the volume. Okay, so they gave us the diameter, but when we're dealing with cylindrical objects, we really need the radius, and we know the radius has to be half of whatever the diameter is. So you can see right now, I'm just going ahead and finding my radius first. Okay, so again, radius is half of your diameter. And now let's find the volume. So we got our fur, and again, our volume equation for a cylinder is this. And we'll use the same formula for the redwood. Very nice. Except our fur has a radius of 3 and a height of 17. Don't forget this is centimeters. All right, so let's see here. We get 3 squared, which is 9. 9 times 17, and then times pi, and you should get 480.66. And again, that is cubic centimeters. That's an equal sign, by the way. There you go. That's an equal sign. All right, redwood. So again, our radius here though was 4 centimeters. So we square that. Our height was 12 centimeters. 4 squared is 16. So 16 times your height, which is 12, then times pi, and you get 603.185. So I'll just round that up to 0.9 cubic centimeters. So you're probably still thinking, well, Mr. Webb, the redwood has more volume, so of course it's going to be the redwood. But we aren't talking about the density. We're talking right now about the volume. Okay, so let's determine the density. Okay, so the fir, to find their density, is again you take the mass, which was 254 kilograms. Do not ignore the units. Very important, not just for now, but also for physics, chemistry, and any other serious science. Okay, so 254 kilograms, and then divide it by its volume, which we got 480.66 cubic centimeters. All right, so in your calculator, real quick, 254, you should probably be doing this with me, divided by 480.66 cubic centimeters, and you should get a density of 0.528. And again, that's kilograms for every cubic centimeter. Oops. And let's take care of the redwood. Okay, so that redwood density is again the mass, which is 271 kilograms. Do not ignore the units, kilograms, divided by the volume, which was 603.19 cubic centimeters. All right, real quick in your calculator, again, do this with me. 271 divided by 603.19, and that's cubic centimeters. And you should get, this is approximation. I should probably use the approximation symbol, but eh. All right, and that's kilograms per cubic centimeters. But then you realize, wait, 0.528 kilograms per cubic centimeter is greater than 0.449 kilograms per cubic centimeter. So the Douglas fir, all right, Douglas fir is denser. All right, so the fir is denser, and if you dealt with this in real life, after carrying around the two different pieces of wood, you probably realize that, hey, fir feels a little bit more solid, a little bit more serious than redwood. And people actually notice that. If you really want to notice in real life, if you actually chop or cut down a certain tree, you're going to realize, a particular type of wood, the fir is going to be harder to chew into than the redwood. Okay, so believe me, density has a lot to play into that. All right, so calculating population density. We do this for census taking. We do this to figure out, well, how many humans are in this area, because then let's consider logistics, traffic, um, even elections. There's so many different ways we can apply this to the real world. So let's deal with population density. So uh, we're going to look at Burlington, Vermont. Okay, so again, we just basically have to figure out, well, how many people you know, took the census and reported themselves to be there, and then divided by the total area. So let's figure this out. We have this city, Burlington. It's got an area of 160 square kilometers. all right, and a population of 109 people. Basically, all you have to do is take the amount of people divided by the area. So again, 109,000 people divided by 160, and you should get approximately 681 people per square kilometer. That's important to note, just because, again, when you're planning for cities and you're building stuff and you're building freeways, you're not going to build a freeway into a less populated area. You're probably going to build a freeway closer to where more people are, right? So that more people can get through their daily commute. Otherwise, you really are actually just wasting people's time, literally. I think they said something along the line of you spend 1/6 of your life in traffic, and that's not good for certain people, right? So you don't want to design a city where you're literally wasting people's time and money because gas, right? So you have to consider that. All right, so let's look at this example. We got Vermont. Again, we have 626,000 people, and we got a trapezoid. And the area formula for a trapezoid is you take the average of your base and your two bases, because notice how this base is not exactly the same as, from BC to AD, right? So we actually have to average those two. So that's why the 1/2 is there, but you still take and consider your height. Okay, so let's go ahead and do this. Each coordinate grid represents 1 mile. So it looks like these are going by 20s, so 20 miles. Okay, so that's 20. This is 40. Okay, and it looks like they already wrote the 40 there for that base, for the base 1. And then for base 2, we got 20, 40, 60, 80. Very nice. So we got 80 miles there. And our height is, let's see, 120, 140, 160. All right, so 160 is out here for our height. Let's do this real quick. 40 plus 80, that's 120. And then you're dividing by 2 there. And multiply by 160. And you should get 900, or I'm sorry, 9,600, 9,600 square miles. And again, the population they gave us was 626,000 people. And then the area that we got from that trapezoid, right, was 9,600. And let's do this real quick in the calculator, 626,000. Hopefully you're doing this with me, not just watching, staring blankly into the screen, probably not even listening to me. That would be very depressing. And you should get 65.2 persons per square mile. Now, in real life, I would probably go ahead and say 65 or 66 people. Okay, I would actually probably just say 66 people per square mile, taking consideration that you have that point 0.2 population count, and you definitely don't want to miss out on point 0.2 of a population, plus the fluctuation of children that are being born right now and whatnot. You never know if you're growing or decaying, but point 0.2 is a big difference, especially with elections. If you don't include that point 0.2, it'll be like surprise, and everybody's gonna be like, "What? I thought you said there were only this many people." And it's like, "Oh, there's that point 0.2 in this one district in this one county," and then you're just like, "Oh, oops." So yeah, so accuracy really can depend on your context or your situation. All right, so your turn number one. Again, we have a certain amount of people. All right, and we got a parallelogram. But again, a parallelogram, isn't that really just a rectangle, right? I mean, your bases are all the same, just it's just oblique, right? So use the same area formula. And so again, density equals an amount of people divided by your area. And you should get something, okay? So go ahead and let me know what you get after that. Again, look at the grid. It represents 1 mile for each little thing, but if you guys notice, it goes by 5 miles. So 5, 10, 15, 20, 25. Same thing with your y-axis, 5, 10, 15, 20. So make sure you count correctly what your length and width are in reference to the miles. Don't just say it's 2 by 4. It's not 2 by 4. It's, based upon the miles of the grid. So do not ignore that. That'll be a common mistake, especially if you're not listening to me right now. All right. So calculating measures of energy. So we don't just deal with people and objects. We also deal with combustion ratings and heat efficiency. Um, let's just say there's certain gases that we use for certain things. You don't want to use liquid hydrogen for a barbecue, okay? Unless you probably want to explode or you know seriously fry your steak, which would be a travesty. You'd probably use propane. So each different gas has a certain amount of energy, and that certain amount of energy is known as a British thermal unit or a BTU. That's a energy of unit. There's approximate amount of energy needed to increase the temperature of 1 pound of water by 1 degree Fahrenheit. So you aren't going to use like a little tiny lamp tank, right, that you use for like camping to heat up 20-gallon tank of water. It's just not real. It's going to take forever, and if it's cold outside, it's going to take really long. You're probably going to pull out a 5 pound or 5-gallon tank of propane, right? That'll probably light things up. So it really depends on your container. So the amount of energy that can be stored in your container, and that'll probably give you your BTUs per unit of volume. So let's look at an example. We have a spherical tank. It's filled with gas, and its dimensions are shown. So they already give us this tank. They give us the diameter, and again, our diameter is really just two radius, right? So our radius is half of whatever our diameter is, which is 6 feet. So our radius is 3 feet. All right, so we just plug that into our volume formula for our sphere, because again, we got a sphere here. And again, that's just 4/3 pi r cubed. And then you should get 36, and it looks like they left the pi in there. So 36 pi of cubic feet. And we're using natural gas. So one thing to note is they do say it's natural gas. It should provide this many BTUs. All right, so it's like, thanks. So we're going to take that number and divide it by the total volume that we found earlier. Okay, so if you do that, you should get around 1,027 BTUs, and that'll tell us, well, how much is really in that tank. That's important to note because in real life, certain tanks are for certain things, certain gases are for certain things. One reason NASA uses all the hydrogen for their rocket propellant is it's actually it's very light, but yet very combustive, and that's a very efficient fuel to use as opposed to propane or kerosene. Oh, kerosene, that thing wouldn't even take off. So it just depends on, again, how efficient it is in the sense of energy. All right, so let's take a look here. We got this tank, the same tank, all right, which had 36 uh, pi, right? Yeah, 36 pi cubic feet. So it's the same spherical tank, except now it's filled with kerosene. Okay. So the volume, again, we're still using the same old tank. All right. So same amount of volume, but it's filled with a different gas. It's filled or fuel. All right. It's filled with kerosene this time. We used to use those in the olden times, right? So if somebody didn't like electricity, they didn't like gas, they would use this liquid that was very flammable. But it's basically it has that many BTUs. All right, so that's a lot of BTUs. Okay, dang. All right, and let's just use our calculator here. So we have 114,206,000 BTUs divided by 36 pi, and you should get, and actually you could round up because it's zero point 0.7, but you know, there. So technically it's 3 if I round up. But that is a lot, right? That is a lot of BTUs. So if you compare it to our previous example, we only had 1,027 BTUs with natural gas. But look at kerosene. Kerosene is like way more flammable. and efficient in the sense of heat. So kerosene lamps would be a great uh, gas, basically, or liquid, um, to keep you warm at night as opposed to natural gas. So that's something to note, right? Different gases for different things. Just don't spill it. Ooh. And then and it's going to smell too if you get all over the place. Ugh. All right, so your turn number two. Again, we got a cylindrical tank. So again, what's the volume formula for a cylindrical tank? And then how many BTUs will a tank hold if it's filled with natural gas? So please note, natural gas, they gave you this for the BTUs, all right? 116,151 BTUs. And then you're going to divide it by the volume of uh, your cylindrical tank. So find the volume first, and then 116,151 BTUs divided by whatever you got for your volume, and that should show you how many BTUs will that tank provide you with. So once you figure that out, let me know. Homework, page 1051 through 1053, numbers 1 through 11. Let me know if you have any questions, concerns, or headaches. And again, just think real world. All right, it isn't really just memorization of formulas. It's more about understanding the context and what variables you have to consider in order to solve for it. Um, so again, just be aware of context. Um, right? One person might think, "Hey, this door is busted. It's not working," and then you never know. It's like, well, did you check it first? Because I didn't say it wasn't working. All right, have a good one, guys.